So good afternoon. Over the past few years, Dr. Liu and I and our colleagues have worked extensively on the Bigness Compensation. So today is like a summary of what we have done since I came to US. Basically, I will cover three topics, from the basic definition of the atmospheric and oceanic heat transport and to the theoretical analysis of the compensation and the collaboration response between the atmosphere and ocean heat transport. Finally, I will talk about the response of the atmosphere and ocean heat transport on the global warming and, of course, the mechanism behind it. So first, what is atmospheric and oceanic heat transport and what's their importance? We know that the Earth receives solar radiation at the top of the atmosphere, and at the same time it emits outgoing long wave back to the radiation or back to the space to cool itself down. So due to the orbital parameters and albedo, that the tropics receive more solar radiation than the high latitudes. And similarly, the outgoing long wave radiation is much more in the tropics than the high latitudes. Then the net difference between the incoming solar radiation and the outgoing long wave radiation is the net radiation at the top of atmosphere. So in low latitudes, we know that we have more incoming than the outgoing. So in tropics, it has the Earth is receiving energy, but in high latitude, it is opposite. It is because the outgoing long wave radiation is larger than the incoming solar radiation. So Earth is losing energy at high latitudes. Here is a schematic plot of the incoming solar radiation and the outgoing long wave radiation. We know that in the tropics we have the surplus energy, but at high latitudes the Earth is losing energy. So if the Earth is like Mars, so if we don't have the atmosphere and ocean, then the temperature in the tropics will keep increasing until the solar radiation is balanced by the outgoing long wave radiation. And the opposite thing happens in the high latitudes. The temperature will keep decreasing until these two are balanced. But luckily, we have the atmosphere and ocean heat transport. We have atmosphere and ocean. Then these two systems are all transporting the surplus energy in the low latitude to the high latitudes to redistribute the energy in our climate. And here is the heat transport. The black curve is the total heat transport, and the red is the atmosphere heat transport, and the blue is the ocean heat transport. So positive sign means that it transports northward, and a negative sign means it transports southward. If we observe these curves carefully, there are several interesting features there. First, they are largely symmetric along the equator. It is because the net radiation at the top of the atmosphere is largely symmetric along the equator. Second, the ocean heat transport dominates in the deep tropics, but the atmospheric heat transport dominates in the mid to high latitudes. And finally, if we look at it carefully, there we find the northern hemisphere ocean heat transport is larger than the southern hemisphere ocean heat transport. So why do they show these features? And more importantly, how is the energy transported by the atmosphere and the ocean? Let's start from the tropical atmosphere. Basically, the atmospheric heat transport can be understood by two factors: the meridional circulation strength at a moist isotrope surface, denoted by the psi, and the net energy at a moist isotrope surface, denoted as a delta H. The Halley circulation happens to be the meridional circulation at the moist isotrope surface in the tropics. It is because the moist isotrope surface is largely vertical in the tropics. As the contour shows that the northern branch of a Halley circulation is clockwise, and the southern branch of a Halley circulation is anti-clockwise. So we know that the low-level flow is equatorward and the upper-level flow is poleward. And the shading here shows is the energy in the L column. We know that at the top of the atmosphere, the atmosphere has a maximum energy, and at the bottom of atmosphere, the atmosphere has a minimum energy. So since the lower branch of the circulation is equatorward, so the energy transport at the lower atmosphere is equatorward, and the opposite is at the top of the atmosphere. It is transported poleward. And we know that the energy at the top of the atmosphere is much larger than that at the bottom. Plus the circulation strengths at the top and at the bottom are more or less the same. It is because they are on the same contour, so they have the same circulation strength. Therefore, the net the net heat transport is dominant by the upper branch of the Halley circulation and transport poleward in the tropics. When go to the mid latitude, so the dynamics is quite different. The mid latitude atmosphere heat transport is due to the large scale eddies in the westerly jet. If we take a look at the weather map, the dominant feature must be the cyclones and anticyclones. They are moving poleward and eastward. They are trying to mix warm air from the low latitudes and cold air from the high latitudes. So in this case, the energy transport is completed. For example, if we have a cold front or warm front in Columbus, then the local heat transport is completed due to these weather systems. And still, we can use Psi and delta H to understand the mid-latitude atmosphere heat transport. But this time, we need to plot the circulation and strength on the moist isotrope surface, not the height coordinate anymore. And equivalently, we can plot it into the moist potential temperature coordinate. Here is the circulation of the atmosphere. We see that at mid latitudes, the circulation strength is much larger than that in the tropics. So this is why the atmosphere heat transport peaks at mid latitudes. Then, well, we know that there is Halley circulation in the atmosphere. So correspondingly, due to the surface wind stress coupling, there is a subtropical cell in the upper ocean, mostly in the Indian and Pacific Ocean. Same as the atmosphere heat transport, the surface warm water was transported poleward, and less warm water is at the subsurface they transport equatorward. So the net energy transport in the Indian and the Pacific is poleward, and they are largely symmetrical along the equator. It is because the subtropical cell is largely symmetrical along the equator, and somehow the northern part is larger than the southern part is larger than the northern part. It is because in the southern hemisphere we have more ocean there. And unlike the heat transport in India and the Pacific Ocean, in Atlantic Ocean, it has its own critical circulation component, the Zonal hinterland. Sometimes we call the Atlantic Meridional Overturning Circulation, the AMOC. The AMOC is peaks about at depths of 1,000 meters and transports energy all the way northward from its south boundary to the Arctic Sea. So then, if we add the ocean heat transport in the Atlantic and in the India and the Pacific, we know that in the northern hemisphere, since they are all northward, therefore the total ocean heat transport amplifies. But in southern hemisphere, the Atlantic is northward and the India and the Pacific is southward, so they are cancers. This is why we see that the northern hemisphere ocean heat transport is larger than that in the southern hemisphere. And again, we can still use the Psi and net energy to analysis the ocean heat transport. So in this way, right now, we can compare the scale of atmosphere heat transport and the ocean heat transport. For example, in the tropics, since the Halley circulation and the subtropical cell circulation are coupled, and so their strength is more or less the same. But in the tropical ocean, the energy is much larger than that in the atmosphere, so this is why ocean heat transport dominates in the tropics. And in mid-latitude, it is opposite. The circulation strength of atmosphere is much larger than that in the ocean, and the energy is roughly the same. So we know that atmosphere heat transport dominates in mid-latitudes. So here is a summary for section 1 that we know that atmosphere and ocean heat transport are maintaining our current meridional temperature gradients. So this is very important for our lives. And atmosphere and ocean heat transport shows very distinct features over the globe. For example, they are largely symmetrical along the equator, and the ocean heat transport dominates in deep tropics, and atmosphere heat transport dominates in mid to high latitudes. And finally, we see that northern hemisphere ocean heat transport is larger than in the southern hemisphere. It is because of the Magellan circulation transport energy northward in the Atlantic Ocean. So next is the compensation and collaboration between the atmosphere and ocean heat transport response. So the compensation and the compensation between the atmosphere and ocean heat transport response is also called the Bigness Compensation. So it was first hypothesized by Bigness in the 1960s. Bigness raised out this hypothesis when he was studying the NAO. He found that in the lower index of the NAO, we have a stronger atmospheric heat transport but a weaker ocean heat transport. But when it goes to the normal year, that the atmospheric heat transport becomes weaker, but the ocean heat transport becomes stronger. So in this way, that the Bigness compensation states that the atmosphere and ocean heat transport are compensating. Then he says that the anomaly of the heat flux in the ocean and atmosphere are assumed to cancel, leaving the total heat flux and the radiation budget unchanged. Actually, the total heat flux and the radiation budget are changing, but it is very small. So the Bigness compensation are found to be valid on different time scales in different locations and in different climate models. For example, the researchers, when they are studying the multi-decadal North Atlantic oscillation, they found that the response of atmospheric heat transport and ocean heat transport shows negative correlation. That means these two are compensating each other. And then they plot the correlation against the different time scales. They found that the Bigness compensation is mostly obvious at the time scale larger than the decade. And similar results are found in the GFDL model, and they found that the strong negative correlation is on the decadal time scales. And in other studies, they found that, for example, in the Hosing experiment, or we just randomly perturb the model parameters, we found that there is always the reduced ocean heat transport is compensated by the intensified northward atmosphere heat transport. So in a world that the Bigness compensation is a very robust feature for our climate. But sometimes collaboration also happens. The collaboration means that both atmosphere and ocean heat transport, the response of atmosphere and ocean heat transport are in the same direction. That means both of them intensify or reduce. So here's an example. We know that the Halley circulation and the subtropical cell circulation are coupled. Then if the Halley circulation weakens, then the subtropical cell will also weaken. But if other factors don't change, then we will have a reduced atmosphere and ocean heat transport. So in this way, the atmosphere and ocean heat transport response are collaborating. Indeed, in the GCMs, when people perturb the extratropics, for example, they cool the southern hemisphere or remove the Arctic sea ice, they found that the collaborating response is very obvious here. So try to understand why sometimes it is compensation and sometimes it is collaboration. And we use a coupled energy balance model. So the energy balance model is very simple. It is one-dimensional, and the energy in the atmosphere is balanced by the top of atmosphere heat flux and the surface heat flux, and plus the meridional atmosphere heat transport. And in the ocean, it is similar by the solar radiation, surface heat flux, and the ocean heat transport. So even though our model is very simple, but it can produce a very good temperature profile against the observation. And the pro of our model is that it is fully coupled and it has a general forcing there. But the con is that the parameterization of the ocean heat transport is not physically sound. It is because the diffusion scheme works well for the mid-latitude atmosphere, but for the overturning circulation in the ocean, it is not a good choice. But this is the only choice. So since the model is simple, so we can solve out the analytical solution. For example, if we plug the eigenfunction of the solar radiation into our model, we can get the temperature, we can get the heat transport of the atmosphere and ocean. Then if we perturb any model parameters, for example, the KO, the KO is the capability of ocean heat transport. If KO is large, then the ocean is efficient to transport energy. If KO is small, that means ocean is less efficient to transport energy. And BO, BD, and K is very similar parameters. So we found that the compensation ratio is negative. The compensation ratio is defined as the response of atmospheric heat transport over the ocean response of ocean heat transport. So if it is small, that means the response of the atmosphere and ocean heat transport, their sign are different. And if it is positive, that means they are in the same sign, they are collaborating. So here is an example. For example, if we perturb the KO, if KO reduces, we know it is a capability of the ocean heat transport. The capability of ocean heat transport reduces, then we have a reduced ocean heat transport, as the blue curve shows here. So since the ocean heat transport reduces, then there is less energy was transported northward. So in this case, in south, ocean temperature becomes warmer, and in the north, it becomes cooler. So we have a larger ocean temperature gradient. Then the surface heat flux is proportional to the SST. In this case, the surface heat flux has a larger meridional gradient. So in the south, there is more energy goes into the atmosphere, but in the north, there is less energy goes into the atmosphere. So the atmosphere in the south will warm, and in the north will cool. So we have a larger temperature gradient in the atmosphere. Since the temperature gradient in the atmosphere becomes larger, so we have an intensified northward atmosphere heat transport. In this case, these two heat transport response are compensating. And here is another example. If we perturb BO, so the ocean is losing energy, and more energy goes into the atmosphere. So since here we lose energy here, so there is a intensified ocean heat transport. Try to compensate the loss here. And since the atmosphere gains energy here, so a little part goes into the space, and most of them was transported away. So then we have the compensation response. The compensation response actually is a zero-sum game. That means one's loss is another's gain. So in this case, any change at the surface, any changes in the surface heat flux will always trigger the compensation response. So here is an example. We use our simple model idea to try to explain the GCM results. Here is a hosing experiment. The hosing experiment is that people discharge mild water at the North Atlantic to mimic the Heinrich event. So in this case, the AMOC totally collapsed. Then we have a southward ocean heat transport, and at the same time, we have a bipolar seesaw in the surface temperature that the southern hemisphere warms and the northern hemisphere cools. So the temperature gradient in the atmosphere becomes larger. Then in this way, atmosphere tries to transport more energy northward to warm the northern hemisphere up. Therefore, we have a northward atmosphere heat transport. And in this case, so the southward ocean heat transport is compensated by the northward atmosphere heat transport. So this is exactly when we perturb the KO in our simple model. Even though our model is very simple, but I think it captures the essence of the Bigness compensation. We found if we perturb the solar radiation or the feedback at the top of the atmosphere, we found that we have the collaboration response. It is easy to understand. For example, if we perturb the solar radiation at the top of solar constant at the top of the atmosphere, then there is more solar radiation in the tropics. So the tropical atmosphere and the ocean both warms more than the polars. So they will all transport energy poleward. Therefore, they are in the same direction, and they have the collaboration response. Here is a natural experiment from observation when people studying the seasonal cycle of ocean heat heat transport. The x-axis is different months, and the shading is heat transport. Red means northward and blue means southward. So we find that, for example, in boreal winter, both atmosphere and ocean are transporting energy northward, and in boreal summer, that both of them are transporting energy southward. So in this case, the atmosphere and ocean heat transport are collaborating, and which is predicted by our simple model. So the collaboration response is like a win-win game. Any changes at the top of any flux change at the top of atmosphere will also be shared by the atmosphere and ocean system. Then they are always in the same direction to try to, for example, transport the energy away or try to, transport energy to compensate the loss at the top of the atmosphere. So here, why sometimes it is compensation and why it is sometimes it is collaboration? Because the compensation is like a zero-sum game. So flux change at the surface will always lead to the compensation, but the collaboration is a win-win game. So the flux change at the top of atmosphere will shared by the atmosphere and the ocean, and they are always in the same. Therefore, they are always in the same direction. Therefore, it is a collaboration. So right now, I'm going to talk about the response of atmosphere and ocean heat transport on the global warming and the mechanism behind it. Plenty of the previous studies found that on the global warming, we have an intensified atmosphere heat transport and a reduced ocean heat transport. For example, in the core drop CO2 scenario in simple 3, we found that the intensified atmosphere heat transport and the reduced ocean heat transport are largely symmetric along the equator. And this feature is also seen in the different scenarios. For example, in A2 scenario in simple 3 and in RCP 8.5 scenario in the simple 5. But the symmetric compensation response is not obvious. First, in our carbon energy balance model, it is not easy to produce a compensation response. To adapt our model to study the global warming case, we include emissivity in our raw model, and so we just need to perturb the emissivity. Then we can mimic the global warming. But the point is that our model is a dry model. There is no moisture there. Then another is there is no ice albedo feedback. So this positive feedback is very important to produce the polar amplification on the global warming. So first we linearize our energy balance model and keep all parameters as the same as what I showed in the previous slides. And then we perturb the emissivity. So in this case, we found there is no compensation. Both of the atmosphere and ocean heat transport are in the same direction. They are all amplified toward the poleward. It is because under this global warming case, the temperature in the atmosphere and ocean warms more in the tropics than the pole. So this is why they are all transporting energy poleward. Then we try to tune the Ka. Ka is the capability of the atmosphere heat transport. When we found that only if the K is large enough, we can produce a very weak compensation response. It is because when the K is large enough, so the atmosphere can transport more energy poleward to warm the pole or the ocean at high latitudes. In this case, we can produce a very weak polar amplification in the surface ocean. Then we have a very weak compensation response. But this is not real. This is not consistent. This is not as consistent as what we show in the GCM results. Second is that the AMOC is likely to reduce significantly on the global warming. Here is that researchers use a bunch of climate models. They found that on the global warming, the AMOC will reduce significantly. But the reduced AMOC usually leads to an asymmetric compensation response. For example, in the hosing experiment, that we have a southward ocean heat transport and a northward atmosphere heat transport, and they are largely confined in the northern hemisphere. But on the global warming, we see that they are largely symmetric along the equator. So the symmetric compensation response is not obvious. And last is that almost all previous studies use the heat flux to calculate the ocean heat transport. If we take a look at the temperature equation in the ocean, we see that in a stable climate that there is no temperature tendency because it is in the equilibrium. So the flux inferred ocean heat transport is equal to the real dynamic ocean heat transport due to the advections and the nonlinear terms. But on the global warming, we know that CO2 increases, so the heat storage increased significantly. For example, in the observation, people found that the ocean heat content change is changing significantly and linearly. So the temperature tendency would be much larger than the zero. Therefore, the real dynamic ocean heat transport won't be balanced by the flux inferred ocean heat transport. So what is the ocean heat content related heat transport, and what is the role of this? So to try to understand these questions, we use a simulation from CCSM4, and it was forced by the historical and RCP 8.5 forcings, and it was run from the pre-industry to the end of 26th century. Here is the atmosphere and ocean heat transport of the 21st century and the 26th century compared to the 20th century. So first, I use a conventional calculation scheme, use surface heat flux to calculate the ocean heat transport response, denoted as OHTFX. And we found that the blue curve. So we found that OHTFX and AHT response are largely symmetric along the equator. So this is consistent with previous results. And then I use the product of velocity, meridional velocity and temperature and plus nonlinear terms to calculate the dynamic ocean heat transport, the real ocean heat transport change. So we found that the real ocean heat transport change is very different from the flux inferred ocean heat transport change. So in northern hemisphere, it has a much more response than in the southern hemisphere. Then the difference between the flux inferred ocean heat transport and the real ocean heat transport is the heat content related ocean heat transport. So it emerges from the extratropics in southern hemisphere and transport energy all the way northward. And we further find that go to the 26th century, that we found the response are all confined in the northern hemisphere, and the heat content related ocean heat transport is close to zero, because in the global warming, the climate goes into another equilibrium. Therefore, there is no temperature tendency there, so it is close to zero. Here is a summary of the features of atmosphere and ocean heat transport response in 26th century and 21st century and 26th century. First, they are largely symmetric along the equator, consistent with previous results. And second, that we found that the heat content related ocean heat transport is northward, but the real dynamic ocean heat transport has more response in northern hemisphere than in southern hemisphere. And when it goes to the 26th century, that the response are almost confined in the northern hemisphere, and the heat content related ocean heat transport is ignorable. So while atmospheric heat transport intensifies and ocean heat transport reduces, dynamically, not the flux inferred. And then what is the heat content related ocean heat transport? Finally, is why they shows a symmetric compensation response on the global warming. So first, let's start from the intensified poleward atmosphere heat transport. The energy in the atmosphere basically is a moist static energy. It includes the internal energy, potential energy, and the latent energy. So when we combine the potential energy and the internal energy, so it is a drastic energy. It corresponds to drastic energy transport, and the latent energy corresponds to the latent energy transport. The summation of the drastic energy transport and the latent energy transport is the atmosphere heat transport, so the total atmosphere energy transport. We found in 21st century, the response is in the tropics, it is dominant by drastic energy, and in extratropics, it is dominant by the latent energy transport. The mechanism is like this. There are three mechanisms in the tropics lead to atmosphere heat transport change. Two of them lead to a reduced atmosphere heat transport, and one of them lead to an intensified atmosphere heat transport change. On the global warming, the temperature increase, then we have more moisture in the atmosphere. So the moisture was transported equatorward due to the trade wind and goes to the deep tropics. Then it triggers stronger convection. So we have a higher tropopause. Therefore, we have higher drastic energy in the atmosphere, as the shading shows. So the increased drastic energy is advected by the mean Halley circulation, therefore leads to intensified drastic energy transport. But at the same time, since Q increases, so we have more equator latent energy transport. And plus, under global warming, we know that Halley circulation will also weaken. So the weakened Halley circulation will also induce or reduce drastic energy transport. When we combine all these factors together, we found it is dominated by the increased drastic energy, therefore leads to intensified poleward atmosphere heat transport in the tropics. If we go to mid latitudes, we find it is due to that temperature gradient in the mid-troposphere becomes larger, so the baroclinicity in the atmosphere becomes larger. So in this way, we have stronger storm tracks. So that leads to an intensified latent energy transport in mid latitudes. But at the same time, under global warming, the tropopause becomes lower. So in this case, we have a reduced drastic energy transport. But if we combine them together, we found it is dominant by the latent energy transport. So in mid latitudes, we have an increased atmosphere heat intensified. So in short, in tropics, it is due to the intensified drastic energy transport, but in mid latitudes, it is due to intensified latent energy transport that leads to an intensified poleward atmosphere heat transport. So same idea. We also try to decompose ocean heat, real poleward ocean heat transport first into different basins, then into different circulation systems. For example, the red is into sail transport, and the orange is a gyre, and the purple is the eddy. So the sail is the overturning circulation in the ocean, and the gyre is a large-scale horizontal circulation, and the eddy is very small-scale circulation. So we found over the globe, the ocean heat transport response is dominated by the sail heat transport, and in different ocean basins, it is also dominated by the sail heat transport. Therefore, the sail heat transport is playing the dominant role for the real dynamic ocean heat transport response, and the gyre and eddy are playing the secondary role. We know that the sail heat transport plays the dominant role, so we can further try to decompose the sail heat transport into two parts. First, the perturbed temperature over the mean circulation, denoted as the dotted line, and the second is the perturbed circulation on the mean temperature, denoted as a dashed line. So let's start from the Indian and the Pacific Ocean. We know that under global warming, the surface water warms more than the subsurface water. So in this case, the surface warm water is advected by the mean subtropical sail. So therefore we have an intensified poleward ocean heat transport in India and the Pacific, as denoted by the dotted line. But at the same time, due to Halley circulation weaken, so the subtropical sail also weakens. Then the weakened subtropical sail will also lead to a reduced ocean heat transport, denoted as a dashed line. So when we combine them together, we found that it is dominated by the circulation. Therefore, we have a reduced ocean heat transport in the Indian and the Pacific Ocean. And the same mechanism holds in the Atlantic Ocean. We found that it is due to reduced AMOC that leads to a reduced ocean heat transport, even though the global warming leads to an intensified northward ocean heat transport. But the mechanism changed when we moved to the Southern Ocean. We found that first, the Deacon sail, the strength of Deacon sail doesn't change too much. So we don't have ocean heat transport response in the Southern Ocean here, as denoted by the TDV. But since the surface water warms a lot, so they are all advected by the mean Deacon sail. In this way, we have an intensified northward ocean heat transport, and we see so that means a reduced southward ocean heat transport in southern hemisphere. Another interesting issue is that if we combine the atmosphere and ocean together, we know that the Halley circulation and subtropical cell circulation both are weakened. Therefore, the weakening of the circulation leads to a reduced atmosphere heat transport and a reduced ocean heat transport. In this case, they are collaborating. And at the same time, due to global warming, the energy in the atmosphere becomes larger, and the temperature in the ocean also becomes larger. Therefore, in this way, they are all lead to an intensified polar atmosphere and ocean heat transport. But since the mechanism, the dominant mechanism in the atmosphere and ocean are different. So in the atmosphere, it is due to VDT, but in the ocean, it is due to TdV. So these two collaboration responses lead to the compensation response in the tropics. I have talked about the mechanism of the dynamical atmosphere and ocean heat transport. Right now, I want to talk about the ocean heat content related heat transport. Basically, we call it the apparent ocean heat transport. The apparent ocean heat transport is actually caused by the inhomogeneous heat uptake by the ocean in the southern ocean. So, unlike the global warming, the polar application in the surface air temperature, the ocean heat content change in the 21st century is more visible in the Southern Ocean and the North Atlantic. When we take a look at the zonal average of the ocean heat content change in 21st century, we see there are two peaks in the mid latitudes. One corresponds to the North Atlantic and another corresponds to the Southern Ocean. When we integrate these abnormal ocean heat content zonally, we have the total ocean heat content change. Therefore, there are only one peak there. It is the Southern Ocean. It is because the Southern Ocean has a wider ocean basin there. And so the apparent ocean heat transport can be understood in this way. Relative to the global mean is the blue vertical line here. This is surplus of heat. The surplus of heat means that the heat in the Southern Ocean can potentially be transported into regions of heat less than the global mean. The regions of heat less than the global mean is actually in the blue box in the Arctic Sea. So that means the surplus energy in the Southern Ocean can be transported northward to the Arctic Ocean. That is exactly what we see here, that the apparent ocean heat transport originates from the Southern Ocean and transport all the way northward to the Arctic Sea. So in a sense, the apparent ocean heat transport reflects a different response in the southern and the northern hemisphere ocean in response to the symmetric heat flux. So, for example, in North Atlantic, when the energy goes into the ocean, it was transported away. But when the energy goes into the Southern Ocean, then the energy was trapped there, become the ocean heat content. Therefore, we have this apparent ocean heat transport. Right now, we can combine all the response together. We know the inhomogeneous ocean uptake leads to a northward apparent ocean heat transport, and we know the reduced AMOC leads to a largely southward dynamic ocean heat transport, and they are likely to cancel and lead to a symmetric ocean heat flux inferred from the surface heat flux. And at the same time, we know that the Halley circulation and the subtropical cell circulation are coupling, and they lead to a symmetric response of the atmosphere and ocean heat transport. So in this way, on the global warming, why they shows a symmetric compensation response, it is because these two are cancers, and eventually it is expressed as the coupled Halley circulation and the subtropical cell response. Then the apparent ocean heat transport and the symmetric compensation response are also found in the SIM5 models or in the CSM large ensemble model. In the CSM large ensemble, we picked up 15 models from SIM5, and we found that the northward ocean apparent ocean heat transport and the symmetric compensation response, it is valid in the SIM5 and CSM large ensemble. We also try to diagnose the reduced real ocean heat transport in the CESM large ensemble. We found first, the global ocean heat transport response is due to the cell heat transport. Then in the Indian Pacific and Atlantic Ocean, it is due to reduced circulation. But in the Southern Ocean, it is all due to the warming. So what would happen after the 21st century that we see after the 21st century that the response of atmospheric heat transport in northern hemisphere and in northern hemisphere will keep increasing, but the response in southern hemisphere will disappear. So at the end of 26th century, we see that the response is largely confined in the northern hemisphere when the global temperature warms more than 10 degrees and the AMOC is totally collapsed. So the mechanism is due to, after the 21st century, the Halley circulation and the subtropical cell circulation in the northern hemisphere keeps reducing, but the Halley circulation and the subtropical cell circulation in southern hemisphere, they recovers. So this is why we don't have any response here in the southern hemisphere anymore. So the summary, why atmospheric heat transport increases and ocean heat transport reduces, it is because the drastic energy in the tropics and latent energy in the mid-latitudes, but the ocean heat transport is all due to the cell heat transport. And what is the apparent ocean heat transport? The apparent ocean heat transport is due to the inhomogeneous heat uptake by the ocean. It reflects the very different response to the symmetric heat flux at the northern and southern hemisphere. And finally, the symmetric compensation is due to that the apparent ocean heat transport cancels the dynamic ocean heat transport, leading to a symmetric heat transport inferred by the heat flux. And this is eventually expressed as a symmetric Hadley and subtropical cell response. So finally, I want to thank Qing Li and Jing Han, my friends, for discussion the heat transport in the in the CS models, and researchers from France and Germany for the discussion in Sim 5 models. So yeah, that's it. Thanks.